Let's say we want to represent the decimal number 25 in binary. That's pretty simple. In decimal, each position in the number refers to a power of 10, while in binary, each position represents a power of 2. So that means, because 25 is equal to 16 plus 8 plus 1, the binary representation of 25 is 11001, because there's a 1 in the 1's column, a 1 in the 8's column, and the 1 in the 16's column. This system works quite well for representing positive integers, but what if we wanted to represent a negative number, like -4? All we have to work with is bits that can either be a 1 or a 0. So we need to find a system in which we can convey the information that a number is negative simply through specific bits being either 1 or 0. The major way that this is accomplished today is using something called 2's complement. But to understand why, it's important to examine two other ways in which this problem could be solved, those being sign magnitude and 1's complement. Hi, my name is Ethan, and I'll be explaining how negative numbers are represented in binary. First, let's look at sign magnitude notation, which is the basis we'll be building off of for 1 and 2's complement. Also, to keep it simple, we're only going to be using 4-bit binary numbers. In sign magnitude notation, the leftmost bit of the binary number, or the bit that has the greatest value when the amount of bits is fixed, is now used as something that's called the signed bit. So, because we're only using 4 bits here, let's start with 0, 0, 0, 0. This bit right here is now, it's not the 8th place, it is now the signed bit. So, this is the signed bit, and all of these 3 bits now represent the magnitude of the number. So if the signed bit is 0, then that means the number is positive, but if the signed bit is a 1, that means the number is negative. This means that if we wanted to go from 7, which in 4-bit binary is 0, 1, 1, 1, to -7, all we'd need to do is flip this sign bit. So 7 is 0, 1, 1, 1, and now 1, 1, 1, 1 is -7, because this signed bit is now 1. One thing to note is, because we're not using the signed bit for its usual value, it means that the range of a signed 4-bit number only extends from -7 to +7, and not from -15 to +15. This approach seems pretty reasonable, because it's pretty much the same as placing a positive or a negative sign in front of the number. If we think of a 0 as just being plus, and a 1 as just being a minus. But yeah, we're all pretty used to this in base 10. However, although it seems reasonable, there are quite a few reasons why this is not the standard notation for negative numbers in binary. First, there are 2 representations for 0. 0, 0, 0, 0, and 1, 0, 0, 0, which in this case means -0? That doesn't seem right. Also, because basic addition and subtraction don't seem to hold up for this notation, let's try subtracting 2 from 7. So it's doing 7 minus 2, or in this case, we're adding -2 to 7. So, in decimal, we know this is 5. We can do this easy. But, in the signed magnitude, we're going to go from 7, which we've already found out is 0, 1, 1, 1, to -2, which is 1, 0, 1, 0. If we add these together, 1, 0, carry the 1, 0, carry the 1, 0, carry the 1, we get 1, 0, 0, 0, 1. That is not 5. So the answer to 7 minus 2 is equal to this, and not 5. And remember, we're only working with 4 bits here, so we can ignore this little overflow bit here. So 7 minus 2 is 1? Clearly, we can see why this would not be the most effective way to represent negative binary numbers, but it does provide the basis for 1 and 2's complements, that being the signed bit. Let's move on to 1's complement, which is an improvement from sign magnitude in that it has a way for addition and subtraction of binary numbers to still work properly. In 1's complement, the idea of a signed bit is still present, where the leftmost bit will be representing whether the number is positive or negative, the same as sign magnitude, where 1 equals negative and 0 equals positive. However, to get from a positive number to the negative representation of that number, we invert every bit in the number. As an example, to go from 2, which in binary is 0, 0, 1, 0, to negative 2, we're just going to be inverting every bit in this number. So this 0 becomes a 1, 0 becomes a 1, 1 becomes a 0, 0 becomes a 1. So, yeah, the negative representation of 2 is 1, 1, 0, 1. The name 1's complement alludes to the fact that if you add a positive number and the negative representation of that number, then we're going to get all 1s. Let's try it here. 0, 0, 1, 0 plus 1, 1, 0, 1 is 1, 1, 1, 1. However, even in this system, we still have negative 0. Both 0, 0, 0, 0 and 1, 1, 1, 1 both represent 0. So there's still some more work we have to do here to get rid of this weird negative 0. Don't like that. But addition and subtraction still hold up when using 1's complement, with one little extra step over normal binary addition and subtraction. To illustrate this, let's look at the same example that we used for sign magnitude, 7 minus 2. So in 1's complement, 2, negative 2 is 1, 1, 0, 1, as we found here, and we add it to 7, or 0, 1, 1, 1 in binary, plus 1, 1, 0, 1. Let's add these together. Plus 1 is 0, carry the 1, 0, carry the 1, 3, carry the 1, 1, 0, carry the 1. And now we have 1, 0, 1, 0, 0. But remember how we just discarded this leftmost bit last time? In 1's complement, we're actually going to be adding that leftmost bit as our final step. So, because 7 minus 2 is 1, 0, 1, 0, 0, we're going to add 1 to 0, 1, 0, 0, which gets us 0, 1, 0, 1, which equals 5. Finally, we're able to add and subtract binary numbers within this range. It's still kind of weird, though, but it works. But having to carry the overflow bit and add it to the end sounds like a strange step to implement into a computer when using negative numbers. And we still have that pesky negative 0. So let's look at the way it's done now, which is 2's complement. To show what 2's complement is, let's first look at a pattern when we're adding and subtracting in 1's complement. When we added 7 and negative 2, we got 0, 1, 0, 0 before we did the carry, and 0, 1, 0, 0 is equal to 4. If we add 3 and negative 3, it's going to equal 0, but in binary, it's going to be 0, 0, 1, 1 plus 1, 1, 0, 0. It's going to be 1, 1, 1, 1, which is negative 0. So, do you notice this pattern here? When we're using negative numbers in addition or subtraction, we're always adding 1 at the end with the carry, if you think about negative 0 being 1 away from 0. So, why don't we just automatically add the 1 when we have a negative number? This is the idea of 2's complement. To find the negative binary representation of a number in the 2's complement system, there are 2 steps. First, take the 1's complement of the number, which is just flipping every bit. Second, add 1 to this number. So, for example, if we wanted to go from 4 to negative 4, 4 is 0, 1, 0, 0. First, we're going to flip every bit. So that's going to be 1, 0, 1, 1. And then we're just going to add 1 to that. It's going to get us 0, carry the 1, 0, carry the 1, 1, 1. 1, 1, 0, 0. 2's complement, this is negative 4. So, this simple trick finally kills negative 0. Look, if we take 0, 0, 0, 0, we flip every bit, so it becomes 1, 1, 1, 1, and we add 1 to that, that's going to get us 1, 0, 0, 0, 0, and in 2's complement, we can just ignore this overflow bit, which gets us right back to 0. So the negative version of 0 is 0. Finally, we've gotten rid of that weird negative 0. There is one quirk, though. Because a 4-bit binary number has 16 possible values, and we've only assigned a value to 15 of those being 1 to 7, negative 1 through negative 7, and 0, we still have one more thing to assign, 1, 0, 0, 0. In this system, we'll assign it to the greatest possible negative number, in this case being negative 8. And we'll come back to that in a minute. But first, let's try some adding and subtracting with 2's complement. 6 plus negative 1 would be 0, 1, 1, 0, plus 1, 1, 1, 1, which is 1, 0, carry the 1, 1, carry the 1, 0, carry the 1, and we can ignore this overflow bit, which gets us 0, 1, 0, 1, which is 5. And if we add 4 and negative 4, it's going to come out to 0 in decimal, but 4 is 0, 1, 0, 0, plus 1, 1, 0, 0, so 0, 0, 0, carry the 1, 0, carry the 1, ignore that overflow bit, and we get 0. There is also an easy way to convert a binary number into its negative counterpart using 2's complement. First, write out the number and read it starting from its right-hand side. Once you've encountered the first 1 bit, invert all bits to the left of that. And now you have the negative complement of that number. Let's try it with going from 4 to negative 4. 4 is represented by 0, 1, 0, 0. And now let's start over here. 0, 0, 1. We found the first 1 bit, so we're going to flip all the bits to the left of it, which in this case is just this 0. So negative 4 equals 1, 1, 0, 0, which is consistent with how we found it before. Now let's come back to this weird thing here, where 1, 0, 0, 0 is equal to negative 8. It's still kind of weird since we don't have a number that represents positive 8. Let's look closer at that signed bit, which has only represented whether a number is negative or not in both the sign magnitude and 1's complement systems. In 2's complement, this actually represents that greatest negative integer. In this case, this is why 1, 0, 0, 0 represents negative 8, because there's a 1 in the negative 8's place. This is consistent with how other negative numbers are represented. Let's take a look at 1, which we've found before is represented by, negative 1, which we found before is represented by 1, 1, 1, 1. Now if we look at this in binary, this is the 1's place, this is the 2's place, this is the 4's place, and this is the negative 8's place. So in this case, negative 1 equals negative 8 plus 4 plus 2 plus 1, which is negative 1. So 2's complement solves both issues that we've had for both sign magnitude and 1's complement, being that there are 2 representations for 0, and also that addition and subtraction don't work very intuitively. The one issue is that operating with the most negative number, in our case negative 8, has some weird side effects. In our case, with negative 8, if we wanted to find the positive counterpart to negative 8, which is 1, 0, 0, 0, we would invert all the bits to get 0, 1, 1, 1, add 1, and it would just come right back to 1, 0, 0, 0, which is still negative 8, because we don't have any way to represent positive 8. Computers and programming languages today have safeguards in place when working with the most negative number. 2's complement first started appearing in computers in the 1950s, and by the 1970s, it was by far the most common way for a computer to store negative binary values. Thank you.